Okay, guys, we're going to go ahead and get started. Welcome to ARC401, Serverless Architectural Patterns and Best Practices. Thank you. My name is Drew Dennis, and with me today, you guys are lucky, Maitreya Ranganath is going to be here to help me out. We're both AWS solution architects based in Dallas, Texas. Our agenda today is to focus on 4 primary macro serverless patterns. We'll start off with a web application pattern, which is also applicable to mobile backends, microservices, or API deployments. Then I'll talk about a data lake pattern, which is new for this year. Talk about some specific sub-patterns related to cataloging and analytical processing of your data in the data lake. And then Maitreya will come up and talk about stream processing and operations automation. But before we get into those items, I want to cover some foundational concepts related to serverless applications that are applicable to all of the patterns we'll be discussing today. All of these patterns are well adopted and well used by AWS customers today, so there's no smoke and mirrors at all going on. These are all referenceable, and we'll talk about some references as we go. So let's start off with a little bit about what a serverless application is. As you all know, on AWS, there are many choices or platforms you can choose from to deploy your applications. Certainly, you can deploy them in virtual machines on EC2. You can deploy them inside of Docker containers on EC2 with a service like ECS. And then there's this class of services that's kind of in the middle called managed services. And these are services where you may not really be responsible for servers, but servers still exist. Servers are still important when you consume that service because you need to be able to right-size that service, potentially scale that service, and you do that by defining the number of servers you're going to be using. And then on the right, you see the class of services that we're going to be focusing on today, which are serverless services, where servers are not present at all in the consumption of those services. So you're reducing your operational overhead because of that, so no operating systems to manage. So there are 4 common tenets that anyone from AWS will adhere to when they talk about serverless applications. Again, no servers to provision or manage, but also you never pay for idle with serverless applications. So if your application is cyclical in nature, maybe you do a lot of end-of-month processing, you don't pay for those times when it's not in use. Also, serverless applications have built-in high availability and disaster recovery. All of the serverless services we'll be talking about today sit at a regional level within AWS. So they automatically span all availability zones to provide you that built-in high availability and disaster recovery. These are really, really big things you had to wrestle with prior to serverless applications. And then perhaps the most important aspect of a serverless application is it scales with usage. So as user requests that are coming in grow, or maybe as data is entering your application and that amount of data grows, the serverless application will scale as well. And we really shift from having servers be the core or the focus and the unit of scale to now Lambda functions being the core and the unit of scale for these applications. So because of that, it's really important to speak a little bit about how Lambda functions behave. When you first invoke a Lambda function, it goes through a process that we'll call a cold start process that I'm sure many of you have heard of before. This involves downloading code to Lambda, starting it up in a container on a Lambda host, and then running any initialization code that you've defined inside of your Lambda function. So you can see in this example, I'm importing some external libraries. I'm actually making a connection to an RDS database, in a relational database, in this case RDS, and I'm doing all of that outside of the handler. So that happens only during the cold start process. And then Lambda will keep the container within which all that code runs available for a period of time so that as subsequent invocations come into that Lambda function, it will be warm. And all of that stuff will have already executed so you don't have to go through that again. So it's really important to take advantage of container reuse as much as you can in your serverless applications. It makes them more performant. Each subsequent invocation, as long as it is warm, will just happen at the handler that you can see highlighted here in blue. If cold start times are an issue for your application, you can always keep them warm by scheduling them with CloudWatch events. That's a very common practice. And also keep in mind you can attach elastic network interfaces or ENIs to your Lambda functions to allow them to communicate with private resources inside of your VPC. And this is a very common practice as well, but should only be used if it's needed to communicate with those private VPC resources, as it will actually add to the cold start times. A few other Lambda best practices. You definitely want to minimize your package sizes to only include necessities. Some AWS SDKs like Java and .NET are kind of modular, so you can just bring over the components of that you need, and the same is true with third-party libraries where applicable. It's always the best practice to separate the Lambda handler that we just talked about from your core logic of your function. Typically, a Lambda handler is going to process an incoming event, and your code is going to be separate from that. So put it in an outside function from the handler so that you can get better instrumentation and unit testing of your code. Leverage environment variables as much as possible. Last time we were up here, this had not been released yet, or at least we weren't available to talk about it at that point. But environment variables is a fantastic way to change the configuration of your Lambda functions and change the way your code behaves without directly changing the code inside the function. It's always recommended to self-contained dependencies. You know, we include some libraries with Lambda, with the service itself, like AWS SDKs. And sometimes you might have a version mismatch. So for that reason, we always recommend self-containing your dependencies in your package as much as possible. Keep in mind that Lambda has a single knob for sizing the resources that are available to that Lambda function. It's a memory knob, but by dialing that up or down, you're also affecting the amount of CPU that's associated to that Lambda function. So by dialing it up, you can really improve your cold start times, as an example, and the performance of your Lambda function. And remember, there's a max memory use statistic that's reported in CloudWatch logs for every invocation, so you can leverage that to make sure your Lambda functions are right-sized. Another way to get great insight into your Lambda functions is to leverage AWS X-Ray. It's very easy to implement. There's some tight integration with Lambda. There's just a checkbox with Lambda configurations to enable active tracing. And this will immediately be able to give you insight into how your Lambda functions and the Lambda service itself is performing. By default, X-Ray will sample 1 invocation per second and then 5% thereafter. And X-Ray will also provide kind of what I call an airport delay map. If any of you have ever seen the US map with airports spread across it, and it will show you kind of in a graph of the amount of delays and the amount of cancellations that each airport is experiencing. You get kind of that same kind of map with X-Ray for service interactions. So as upstream and downstream services with AWS X-Ray, upstream and downstream of your Lambda function, you can get a nice map to kind of see average times and execution latencies. There's also a way to kind of customize the sampling rate and enable this downstream communication in your X-ray traces. So I've included a quick code sample to show you how to do that. I realize this may be hard to see from up at the top, but the second line here in this code sample is actually including a sample JSON configuration file to configure a custom sampling interval control for your X-ray traces. And then the third line, you'll see we actually wrap the require statement for your AWS SDK with X-Ray so that as you instantiate AWS clients, like in this case S3, it will be instrumented and downstream calls will be instrumented with X-Ray. Here's a quick example of what's produced in X-Ray for a Lambda function. The top half of this graph is actually pertinent to the Lambda service itself, and you can see dwell time as an example, or how long a function waited for the Lambda service to begin executing. And then you can see the entire duration of your Lambda function executing from start to finish with respect to the service. Below that is specific to your function. So here you start with the initialization phase, the code that we talked about outside of the handler and how long that executes, and then the handler and the rest, any downstream calls, in this case S3 that you see. And you see a bit of a gap from from when the Lambda service started invoking your function to when the initialization code starts executing in your function, and that can be attributed to those cold start issues that we talked about before in this example. I also want to talk a little bit foundationally about deployments and modeling your serverless applications. You know, it used to be, before serverless applications got really, really popular, that you could kind of leverage CloudFormation to define Lambda and API gateway methods. But as serverless applications became more complex, you know, with hundreds or potentially thousands of Lambda functions, then we recognized a need to provide a more effective way with less verbosity to model your applications. And that's why we came up with SAM. SAM is built on top of CloudFormation, which is really good news because any third-party tool that supports CloudFormation will inherently work with SAM. SAM also supports a lot of the great CloudFormation features like parameters and intrinsic functions, and you can combine serverless or SAM resources and notations with traditional CloudFormation resources and notations, so very flexible. SAM also includes some ways to deploy your application. It will provide a unique artifact for deployment and load that up into S3, and then it will leverage CloudFormation to take that and deploy that into the CloudFormation service as a change set. You also may have heard this summer we announced the public beta of SAM Local, and we're really excited about this because we received a lot of your feedback about providing an effective way to do local testing of your Lambda functions before you deploy them into the service. And that's exactly the use case that SAM Local aims to address. So you can develop and test mock events, test your Lambda functions, and we even give you a local copy of API Gateway that you can spin up that supports hot reloading so you can change your code kind of on the fly and test them. And once your unit tests are kind of complete locally, SAM Local has a CLI that actually includes all of the SAM commands to package and deploy your application to the service. And of course, probably the best way within AWS to deploy CloudFormation templates in a custom pipeline is Code Pipeline. This is our continuous integration service, so it has built-in support now for SAM templates and code CloudFormation templates. You can also integrate additional stages and custom stages in your pipeline, for example, code build stages to do building and potentially testing stages as well. And you can leverage Code Pipeline to deploy to multiple environments. So if, for example, you want to do some testing in a development environment, and then if tests pass, automatically deploy into a staging environment, and then potentially have a manual approval if tests pass there before it goes in production. All of those types of scenarios are supported with Code Pipeline. And also I want to mention a new capability within Lambda that provides the ability to have a Lambda alias mapped to multiple Lambda function versions. And this is really important for Canary deployments that you can do now with Lambda. So now you can define in your SAM templates multiple function versions and specify an amount of traffic and an interval at which traffic will move over from one version to another for your Canary-based deployments. And this is fully supported by Code Deploy. Code Deploy will actually monitor CloudWatch alerts for failures in your newer Lambda function, and if failures occur, it will also initiate a rollback for you. So we're really excited to have this available to your deployments as well. Okay, let's go ahead and start talking about our first pattern, which is the web application pattern. This is the common pattern where you have static content above the top in this diagram, maybe some resources in S3 that's provided and delivered through our content delivery network, CloudFront. At the bottom, you might have your more dynamic calls and content going through API Gateway APIs, backed by Lambda functions potentially, although they could be backed by something else. And then have Lambda itself call other downstream services, like in this case, DynamoDB. And it's really important not to leave out Cognito in this pattern, because Cognito is what can provide sign up and sign in to your applications, as well as identity federation across many internal as well as web identity providers. So this pattern is well used and well adopted across a lot of different websites today. One that I want to specifically call out is Bustle. I don't know if any of you guys have checked out bustle.com. I encourage you to do so. It's a great news, entertainment, lifestyle website targeted at women. And Bustle ran on a traditional infrastructure and moved over to a serverless environment and realized 84% savings in their operational costs. In fact, the CTO here is quoted as saying they really don't need to worry too much about operational overhead anymore. And that speaks directly to the lack of servers that you have to be concerned with, the built-in HA and DR capabilities that we talked about before. Now, security with serverless applications is also worth discussing because it's a little bit different from traditional applications. Each of these services that we've talked about in this pattern has a lot of security features, so we won't be able to go over all of them, but I'll call a few out. There's an origin access identity capability with CloudFront to ensure that only CloudFront can access the resources that are stored inside your S3 bucket. Both CloudFront and API Gateway now support AWS Certificate Manager or ACM TLS certificates. So that makes life a lot easier now to create custom domain names and manage the TLS certificates for those domain names for your API Gateway and CloudFront endpoints. And then, of course, we heavily leverage IAM to make sure that API Gateway has privileges to call Lambda functions and that Lambda functions have an execution role that they can leverage to call downstream services. Now, one of the most important topics when we talk about security is authorization of your API Gateway methods. And there's many different ways to do that with API Gateway. Probably the most common is, as I mentioned before, IAM authorization. So the caller of that API needs to have IAM credentials in order to make that call successful and to get access to that particular method. And there's a few different ways to leverage Cognito to provide those IAM credentials. And we'll talk about a few scenarios related to that here in just a minute. In addition to IAM authorization, there's also custom authorization capabilities with API Gateway. And this involves a Lambda function that you're responsible for, and the sole purpose of that Lambda function is to return an IAM policy that it can validate with the IAM service to provide access to that particular method to go ahead and execute the Lambda function, in this case, behind that API method. Now, there's two types of custom authorizers with API Gateway. A token request type, where a token is included in an authorization header for that request. And this enables you to implement strategies like JWT validation or OAuth provider callouts, so you can contact OpenID or Cognito providers to validate the tokens in those requests. There's also a request type that gives you a little more customizability and flexibility. So beyond just using that authorization header, you can use all headers in the request, as well as query strings, stage variables, and context variables. So if you wanted to, for example, have different authentication schemes or strategies across different stages of your application, maybe dev would authorize a certain way, but in production we'd authorize a different way, you can achieve those types of scenarios with a request authorizer. Let's talk specifically about Cognito and how it enables some of the authorization scenarios we just talked about. In this particular slide, we have 3 users over on the left side, and user A authenticates to a web identity provider. This could be Google, Facebook, Amazon.com even. And that web identity provider provides a token back to the user that it uses to send to Cognito and exchange that for an IAM credential, essentially through a role. So this is a very common pattern to get IAM authorization based on a web identity provider and get access to, in this case, a /web resource that's defined inside of your API. Another scenario, user B, is actually defined inside of Cognito user pools. This is a directory of users and groups that you can maintain inside of AWS. And the flow here is very similar to the previous, where I exchange a token from authentication for IAM credentials, and I leverage Cognito identity providers to do that. And this also gives me a way to implement IAM authorization. But what's really nice about this flow is I can leverage group memberships and attributes to get a role from IAM to give me access to make those calls. So if I'm a member of a certain group, or maybe I'm in the engineering department, then I can get access to those IAM roles. And then lastly, there's built-in support in API Gateway for a Cognito user pools authorizer. So this is separate from the custom authorizers and the IAM authorizers that we talked about previously, a specific type designed for Cognito user pools where the JSON web token that you receive from authentication can be validated directly to give you access to your resource. Also, about a month ago, we had a really big announcement around regional endpoints with API Gateway, and this is decoupling API Gateway from CloudFront. It's a really big release because it enables multi-region serverless applications now. With this pattern, you can actually create regional endpoints for API Gateway in, as you can see here, separate regions. And each of these can be associated with the same custom domain name. And then you can use weighted routing, for example, with CNAMEs in a DNS service like Route 53 to direct traffic from a request for the same name, in this case, api.mycorp.com. And you could use weighted routing to direct all of the requests potentially to one region, and if there's a failover, you could automatically send those requests down to the other region, or you could implement an active-active strategy where both regions are experiencing a portion of the weighting. And then lastly, I just want to mention a few frameworks that are available to help you adopt serverless web applications. The first, for the Python developers in the audience that are familiar with a decorator-based API, is Chalice. Chalice allows you to model APIs and API paths with Lambda functions and deploy an application from Python code into a serverless environment. And then if you have existing Node.js Express applications or Java applications written in a number of different web frameworks, we have built-in libraries and frameworks inside of GitHub to convert those over into the AWS serverless platform. Okay, now let's talk about pattern 2, which is our data lake pattern. Now, one thing that's for sure when you think about data analytics and processing data, and that is your needs around that are probably going to change at some point in the future. They don't usually stay consistent. And that's really why adopting a data lake is so important, because it sets the foundational components for you to be more agile. One of the common tenets of a data lake is to get all of your organizational data into that data lake. You may not know exactly what you're going to do with that, but very low barriers to entry to get that data in. And then a data lake should implement a schema on read strategy so that as you request that data and interact with that data and ask questions of it, you can specify the schema to do so. So in the future, when new questions arise that you need to gain from your data, you'll be able to do that with the schema on read approach. So a data lake should be a home for all types of data, whether structured, semi-structured, or completely unstructured. It should support BI and analytical use cases that are very traditional, as well as some of the more modern predictive analytics based on machine learning. And it's very complementary to an enterprise data warehouse. So data lakes are very commonly used as staging areas into those data warehouses for analytical purposes. So we definitely don't see these as competitive things. And then lastly, a serverless data lake should implement decoupled compute and storage. So you can have multiple layers of a compute environment, multiple compute environments working across the same data. And each of those layers can scale independently from each other, and they can be transient, right? So you can only pay for them during executions. At the center, here's a look at the serverless data lake architecture. At the center of the architecture is S3, which has a lot of great features relative to a data lake pattern that we'll discuss. Obviously, a data lake needs to be able to accept data in a lot of different forms, so ingest is very important. Maitri is going to talk in very good detail about stream processing and ingesting data in great volumes, so I'm going to leave that portion of that pattern to him. Cataloging and searching is a very important aspect of a data lake. So we'll talk about a couple of patterns that leverage DynamoDB and Elasticsearch, and a pattern that leverages Glue to provide this cataloging and searchability of the data. This is all about discovering your data that you're delivering into your data lake. And then at its core, analytics and processing is very important, obviously, to a data lake. There are many different serverless services that you can use to do analytics and processing, like Athena and Lambda that we'll discuss in pretty good detail. There's also services that aren't serverless that have a very important role here, so I want to acknowledge tools like EMR in this place as well. There's certainly a security component to a data lake, so you want to be able to manage entitlements and provide access to data to differing users or groups or constituents of your data. You want to be able to encrypt your data, and we have many different ways to do that, whether you're leveraging S3 natively or KMS. You want to be able to audit access to your data, so CloudTrail and some of its new support for S3 come into hand there, and we'll talk about those. And don't forget about Amazon Macie. It's a data classification service for S3, and it will automatically infer the types of data based on the contents of the files that you store in S3. with machine learning algorithms. So you can actually see, if you've got really sensitive information that might contain personally identifiable information, as an example, inside the files stored in S3. And then lastly, you need a user interface for your data lake. So you need a way for users to maybe log into a portal and begin to discover and search the information in your data lake, or possibly a programmatic API that they can use to do those same tasks. And this API interface should obviously adhere to the security that you implemented with IAM. So let's talk a little bit about S3 as a foundation for the data lake. Unlimited volume, so unlimited amounts of storage with S3. That's pretty nice for a data lake. Also, basically no aggregate throughput limits with S3. Basically, the amount of parallel jobs and workers you can have downloading and uploading files from S3, you can grow your bandwidth accordingly. Multiple storage classes, so there's the standard S3 storage class, but also keep in mind infrequent access and even Glacier. So older data that may be stored in your data lake can be handled and moved differently across those layers. And versioning and encryption is fully supported with S3. There's also maybe some lesser known features of S3 that you can take advantage with respect to a data lake, like CloudTrail data events. So not only getting audits of when files are deleted or added to your S3 buckets, but also when files are read. That can be really useful for a data lake. S3 also has built-in analytics and inventory capabilities, so you can see what usage profiles are like across your groups automatically. And you can always get an inventory of the data stored inside of S3, maybe how big that's growing, how many files there are, those types of things. AWS Config also has built-in checks for S3, so that if you're ever concerned that someday somebody might enable public read access on one of your S3 buckets, AWS Config can monitor that and can notify you when that happens. And then lastly, S3 supports object tagging, which is great for chargeback capabilities in a data lake, and storing additional metadata or information about your objects. Now let's talk specifically about cataloging and searching. There's a couple of patterns here to showcase. The first pattern is more of an event-based pattern. So as data arrives in S3, regardless of how it arrives there, I run a Lambda function to store metadata about that file inside a Dynamo. So that could be information about maybe the data set that it's a member of. If this is an IoT use case, it could be information about the device maybe that's sending that data. It could be a history about the versions perhaps of that particular object. And then I have an update stream with DynamoDB streams and a Lambda function that acts on that and sends that information as well as additional information from the source objects into Elasticsearch for searchability to build a searchable index. So a really great way and a well-published way and documented way to provide data cataloging capabilities for a data lake. I've included a link here to a whole Answers article about doing just that. Also, AWS Glue plays a really vital role in this space. AWS Glue can dispatch crawlers, either on a scheduled basis or on demand, that can automatically look inside your files and infer the schema around those files and build a catalog from that information. So this data catalog that Glue builds automatically with these crawlers is actually Hive Metastore compliant, and we've built in support for that with other analytical services like Athena and Redshift Spectrum. So you can immediately create and define tables in those services and begin to query them in your BI tool of your choice like QuickSight. From an analytics and processing perspective related to the data lake, there are a lot of tools that are out there to provide access to S3 information and data and do your analytical and processing workloads. QuickSight is certainly one that comes to mind. There have been a lot of great recent QuickSight releases like geospatial visualizations, HIPAA compliance, and even now the ability to attach ENIs to QuickSight so that you can gain access into private VPC resources. Predictive analytics tools with machine learning, EMR as we mentioned before. AWS Glue also has an ETL component, and that's a great way to process data that's in your data lake before it's imported into analytical stores like Redshift. But I want to focus on a couple of sub-patterns around this piece of the data lake related to Athena and Lambda specifically. First of all, Athena. Athena is our serverless interactive query service, and it provides you a way to submit SQL queries to the data that you have stored in S3. And what's fantastic about Athena is that it is super fast. In this example, we processed 170 gigabytes of data in under 45 seconds executing this query. We even have a couple of group by parameters specified. That's almost 4 gigabytes a second of data that we're processing. It uses Presto as an engine for its data manipulation as a matter of fact. And there's some efficiencies and best practices that you can gain with Athena. I've got a link here to include kind of a top 10 of those, but I want to call out a few of them that are fairly important. First of all, you can leverage Athena to partition your data. Athena is priced based on the amount of data that you scan. So if you can reduce the amount of data that you scan, you're going to save money. And you can do that very effectively by partitioning your data. If your data is stored in an S3 bucket in a path like you see here, Athena will automatically partition your data. So built-in synergies. But you can specify manual partitioning schemes as well. Strongly recommend leveraging columnar data formats for the data that's stored in your S3 data lake. So formats like Parquet, Avro, and Orc. Also, optimization of file sizes becomes very important for the data stored in S3. Is it one big file or is it a lot of small files? If it's a lot of small files, you'll have a lot of overhead interacting with S3 as a service to open and get those files as an example. But if it's just one big file, that may not be enough to give you that parallelism across your compute environments that you need. So that's why it's also really important to use compression formats that support splittable compression. Parquet and Orc also support splittable compression. So those are going to be the best file formats for Athena, without a doubt. But if those are unavailable to you, compression algorithms like gzip or bzip2 are also very good from that perspective. There's also a serverless batch processing pattern that I want to showcase for your analytical processing needs. This is more of a DIY approach where you have a Lambda function that takes your source data and splits it up somehow, maybe by lines or by size, and hands it off to a bunch of mapper functions that run in parallel to process your data and then write results to a persistent store. And then we have a reducer function in this example collecting that data. This is a pattern that's also well leveraged by customers. Fannie Mae actually leverages a pattern very similar to this to process Monte Carlo simulations and cash flow projections for their mortgages. They actually used to do this on more of a server-based approach, and by adopting this approach, they were able to reduce the time it takes to run simulations by a factor of 4. Fannie Mae has a specific session addressing this particular use case, so I won't steal their thunder, but it's SRV317 in case anybody's interested. And especially if you're in the financial industry, I strongly recommend you taking a look at that one. And then lastly, I just want to point out that if you have existing Python code, and maybe you don't want to write the mapping and reducing capabilities like I just showed you in the pattern yourself, you can leverage a library like Pyron to do that for you. It's actually democratizing the horizontal scale of Lambda. So with the default account limit of 1,000 concurrent Lambda functions, you can actually achieve with Pyron about 10 teraflops of peak compute power. That's extremely powerful to do just by taking your existing Python code. And this is also a great library to leverage for interactions with S3. So you can bring data in to S3 or read data from S3 in very, very massively parallel scenarios across many different Lambda functions. The Pyron team actually ran some tests where they achieved 60 gigabytes per second of read and 50 gigabytes per second of write performance. So I've included the link to the Pyron for further reading. Okay, now Maitreya is going to come over and talk about pattern 3. Thank you.
Thank you, Drew. So stream processing, pattern 3. Imagine that you are responsible for designing and operating a highly successful e-commerce website. We just came out of Cyber Monday. You had a great Cyber Monday. You've been collecting clickstream data from all the actions that happen on your website, but you've been processing them on a daily basis, right? So 24 hours after the fact. Your management gives you a challenge. We'd like to bring that time down from a day to a few minutes. So that's a classic example of having to deal with data that's streaming in, and that's a classic example of a stream processing application that I'd like you to keep in mind. So as we look at the characteristics, these characteristics are shared by many different applications, such as clickstream analysis. You have high ingest rates. Imagine the rate of clicks happening on Cyber Monday. You want to do near real-time processing. This is that challenge of trying to bring the latency down from the time an event happens to the time you get the insight. You also have spiky traffic. Obviously, the traffic that you experience on Cyber Monday is likely to be many times higher than your average day in the rest of the year. Once you get a message in, it's very important that you handle that. So message durability is important. And in many cases, since you're trying to recreate the actions a customer took, the order of the messaging is also important. So these are some of the common characteristics of a stream processing application. So let's take a look at the first example of how you would go about meeting your management's needs. This is an example of a stream data ingestion and analytics on the right in terms of an architecture. So the core of this architecture here is Amazon Kinesis Firehose in the middle. So Kinesis Firehose is a service that lets you ingest large amounts of data, buffers them up in micro batches, and delivers them to destination services. So this lets you essentially decouple a high rate of messages coming in to a destination service where you can better deal with batches of data rather than having to deal with them in streams. So what you do here is you can send data in raw record form directly to the Kinesis Firehose APIs, or you can install a Kinesis agent, which will look at your log files. And as new messages come into the log files, it'll post those messages to the Kinesis Firehose delivery stream. Either way, once a record is in the delivery stream, you can actually do transformations on those records. So you can invoke a Lambda function as seen here. You can send the raw records to the Lambda function. And in the function, you can have custom logic. The logic can be to transform the messages, take a record and transform it from, say, a numeric timestamp to a human-readable timestamp, for example. Or you might be able to look up data in a database like DynamoDB. So if you want to pull out information about the user and that you've stored in DynamoDB, you can make a call and enrich the record as you do the transformation. Once the transformation is done, those records are sent back to Kinesis Firehose, and Firehose now makes micro batches of those and delivers them to destination services. So on the right, you see examples of destination services. S3 is an example. You can store your transformed records in batches in S3, or you can send those records directly to Redshift, where they can be loaded into tables and be available for analytics. You can also send those records to Elasticsearch service, where they can be indexed and available for searches, as well as visualization on tools like Kibana. The pattern at the bottom here is also a common thing that we see customers do. This is a feature called source record backup. So when you're doing transformations, you might want to keep a copy of the untransformed raw records, and enabling this feature gets Firehose to send a copy of that to an S3 bucket that you define. Once you set up this type of pipeline, you can also monitor its performance, and you do that by looking at CloudWatch metrics that Firehose publishes. So you can look at metrics that tell you how far behind are you from the head of the queue in terms of delivering messages to S3. So you can tell how much you're falling behind in terms of the messages that are coming in. As you implement this pattern, some best practices. So Firehose has two key parameters you need to tune. One is the buffer size, and the other is the buffer interval. So these two parameters interact together to decide how frequently messages are delivered to the destinations and how big each of those batch records are. So if you bias towards larger objects, obviously you get fewer invocations to things like the transformation Lambda function. You also get fewer invocations to S3 in terms of S3 puts, so your costs can be lower. Firehose also lets you enable compression. So this lets you compress your data as it delivers to the destination, a great idea to reduce your storage cost, as well as to keep your data transfer costs low. We talked about source record backup. It's a great way to troubleshoot issues with your transformation if you have a copy of the raw records. And specifically, if you're loading your data into Redshift, it's a good idea to follow the Redshift data loading best practices. The link is out here. This talks about how you can format your data to make it better and easily suited to load it into Redshift. For example, how to deal with time series data, how to deal with data that is sorted. So do keep that in mind. Let's imagine another scenario. It's again the holiday seasons, and we have sold 1 million connected thermostats. So people have taken these thermostats delivered at home, they've turned them on, and now we want to provide a cloud-based service that takes the data from these thermostats and provides some intelligence to those devices. So obviously, these thermostats are low-power devices, so they don't have much memory, much CPU capacity. They may not even have connectivity all the time. So you want to use a protocol that is optimized for such Internet of Things type devices. So we choose to use MQTT here in this example as that protocol that is well-suited for low-power devices. The server side of that is AWS IoT. So AWS IoT acts as a server side and receives the messages and measurements from the devices over MQTT. Once the messages are in IoT, we can write IoT rules on that. So these rules in SQL determine filtering on the messages that come in. So if you have different message types, such as temperature, humidity, you can use a rule to filter out just the temperature readings and react to those. At the other side of a rule, you can set up what's called an IoT action, which will deliver those messages that come out of the rule to a destination. So in this example, you see destinations such as S3, where you can store the raw images or the raw sensor data that comes in. You can also use the pattern we saw before, where you can send those records to Firehose and have them batched and sent to S3. Or in the middle, you can decide that you want to process them in near real time, and you can deliver those to a Kinesis stream and hook up or create a real-time application to deal with that. So let's look at an example of a real-time application that deals with that. Imagine that we have these sensors. These are temperature sensors. We know temperature tends to be a little noisy. So we want to take those measurements. We want to smooth them out over a 60-second period. So every minute, we want to smooth that out, and then compare that against a threshold that the owner sets. So you might have a threshold of 90 degrees. I might like things cooler, and I might have set my threshold as 80 degrees. But that's a threshold that the user sets. And I want to send an alert when the temperature, the average temperature reading, exceeds the threshold. So this is a pipeline that achieves that. Starting from the left, we have the data that arrived in the Kinesis stream. This could have arrived from the IoT pipeline that we saw in the previous slide. And then we attach that to a Kinesis analytics application. So Kinesis Analytics is a service that lets you perform near real-time analytics on data coming into a stream. And you represent your logic using SQL. So this is streaming SQL. I'll walk you through some of the parts of this. The parts in blue basically set up the source as well as the destination definitions. The parts in yellow set up that 1-minute window over which we want to smooth our data or average the data. And the parts in green represents the aggregation. Right? So this is where we do the sum of the measurements that the sensor sent us. We also count the number of measurements. So this gives us the ability to do an average. And then we are grouping the whole measurement set by the device ID. So the end result of all of this processing is that we get one average measurement set every minute per unique device that is in our fleet, which is what we really wanted. So you can see how simple it is with just a few lines of SQL to represent a pretty complex processing requirement. Once we have those aggregated measurements, we can deliver those to a destination Kinesis stream again and to perform our custom thresholding logic. Right? So this is where we take those average measurements, and then we pull out the user's defined thresholds from DynamoDB, compare the two, and decide if you need to send an alert using SNS. The other thing you see in this diagram is the error stream. So every time you process a stream of messages through Kinesis Analytics, there could be some misformatted records. And what Kinesis Analytics will do is deliver those misformatted or error records to a destination. In this case, we send it to a Firehose delivery stream and store a copy of those records in S3, so we can go back and look at those and try to fix any errors later. So this is a good practice. Let's double-click on the middle part here, where Kinesis streams have triggered Lambda, and see a few best practices around that. One of the things you have to remember when you set this up is that Kinesis streams are scaled in terms of shards. So each shard in Kinesis stream has a certain capacity, 1 megabytes per second in and 2 megabytes per second out. So this is your unit of scale when you configure a Kinesis stream. The important thing to remember is that for each shard that you have in your Kinesis stream, you get one parallel concurrent invocation of Lambda. So it's a one-to-one relationship. So if you have 5 shards, you get 5 parallel Lambda invocations. So this means that you need to code your Lambda function in order to be able to handle the full capacity of a shard within that one parallel invocation. The other thing is you have a tunable parameter called a batch size. This configures how many messages maximum that Kinesis streams will send to one Lambda function invocation. So this sets you that batch size. The default is 100, but often we find that when you have very high throughput applications, you might want to tune that higher. The maximum is 10,000. So the effect of that is you get more messages per invocation, and you can process them all in one invocation. Sometimes you may find that the amount of processing that you want to do in your Lambda function is so much that you can't keep up with the rate of messages coming into one shard, right? In that case, you may want to consider creating a fan-out pattern. In this pattern, you take your Lambda function logic and split it into two parts. The first part is the dispatcher. This is responsible for getting that big batch of messages from Kinesis streams, making smaller batches out of that, and invoking a Lambda processor function for each of those batches in parallel. So that's on the right side. So as you can imagine, you've parallelized more by using this pattern, so you can get a higher throughput, and you can also get potentially lower latency because you're processing an entire large batch in parallel on the right. But if you look at that, when you're processing things in parallel, what you give up is message ordering, right? Whereas before, you would get a set of messages in order in one invocation. Since you're now processing them all in parallel, you can no longer guarantee that you're going to process them in order. So depending upon your requirements, this fan-out pattern might be a good fit or may not be a good fit. An example of a customer that's using the stream processing pattern is Thomson Reuters. They provide news and data feeds to businesses and professionals worldwide. In all these products, they have product teams who wanted to understand how those products were being used. So they wanted to basically do usage analysis tracking. And so they built a product called Product Insight. And this collects all that information, clickstream, and analytics from all their properties, and feeds that through a pipeline similar to what we saw, and generates insights that the product teams can look at and use that insights to improve the products in near real time. So some statistics they shared with us, they're currently tested up to 4,000 requests per second peak. They're also looking at growing that to over 10,000 requests per second peak. That works out to almost 25 billion requests per month. The end-to-end latency they're observing between the time a request comes in to the time they get the insight is less than 10 seconds. And they're very happy to tell us that since they launched this service or product, they haven't lost any records so far since they launched that. So that's an example of a successful stream processing pipeline. Some best practices. So remember, you have to tune the batch size. This lets you invoke less Lambda functions, and you pay less because we charge by the number of invocations in Lambda. It's also important to tune that memory dial. If you tune the memory dial higher, you get more CPU, and that might help you process the messages in one invocation faster and help you keep up with the rate of messages coming from one shard. If you have control over the client side of your processing pipeline, we highly encourage looking at KPL, which is the Kinesis producer library. This is a client-side library. What it does is it locally batches up multiple messages into one Kinesis record. So what that lets you do is fully saturate your Kinesis stream capacity, as well as make much fewer API invocations to the Kinesis stream. So a great idea for you to be able to batch things on the client side before sending it to the stream processing pipeline. Since we're talking about stream processing, there are several related services. We looked at Kinesis streams in much detail. There are also SQS, Simple Queuing Service, and SNS, Simple Notification Service, that can play a role in serverless architectures for stream processing. This chart here aims to compare these services across various dimensions. I just wanted to highlight two of those. Message ordering, for example. So Kinesis stream orders messages strictly within a shard. When you're looking at SQS, the standard queue is best effort, so it doesn't guarantee ordering. But you can also have a FIFO queue, which guarantees ordering within a concept called a message group, while SNS doesn't guarantee ordering at all. Looking at other things like can you go forward and backward in time, Kinesis stream lets you do that through what's called a shard iterator. So you can actually reprocess messages up to the retention period, while SQS and SNS, once you get a notification, it won't be sent back to you again once you acknowledge it successfully, right? So keep that in mind. And depending upon your business requirements, one or more of these use cases will be better fit by one of these services. All right, let's look at pattern 4, which is operations automation. So I'm going to talk to you in more detail about 3 of those patterns. Number 1 is periodic jobs. We all have requirements to do things on a regular basis. We'll look at some examples of that. We have event-triggered workflows. So we want to trigger a complex workflow when an event happens. Or we want to enforce security policies. And we feel that there are other use cases also, like audit and notification, responding to alarms, as well as trying to extend AWS functionality. For example, creating custom auto-scaling. And the best part about using serverless patterns for this is that you can be highly available, scalable, and auditable just by using inherent properties of the services that you're using. Let's look at the first example, which is periodic tasks. So we've all had the case where we need to actually schedule things like EBS snapshots and configure things like how long we want to retain these EBS snapshots. If you have a very large fleet of AWS accounts and you're operating multiple AWS regions, it can be a challenge to coordinate all of that and keep those EBS snapshots going and track all of those over time. So we created a solution called the Ops Automator. The link below actually takes you to a quick start where you can deploy this. It takes the form of 2 templates. The first one you deploy in a master account, which will be where all that logic and tracking happens. And the second set of templates are what you deploy in the slave accounts, where you want to actually trigger the action. So those are the accounts where you have the EBS volumes that you want to snapshot. And the master account is where you define things like properties of the task, the duration, the frequency, and things like that. All of those properties are configured in a DynamoDB table. So the way the process starts is that a CloudWatch event, which is a periodic event, triggers the event handler Lambda function. This function pulls task definition from DynamoDB, looks at the tasks, and decides what it needs to do by invoking one or more event handler or task executor Lambda functions. Those Lambda functions will assume a role in those slave accounts and perform the action that you want. So in order to take EBS snapshots, all you have to do is tag your EC2 instances with this special tag called the Ops Automator task list, set the tag value as create snapshot, and the Lambda function will create a snapshot for that EC2 instance. It will do that across multiple accounts and across multiple regions. The best part about this is it will also track how those tasks went by writing information into DynamoDB as well as into CloudWatch logs. If the process encounters any errors, it will notify you automatically through SNS, so you can receive an email or an SMS. So it's a great way for you to automate commonly occurring periodic tasks. The entire framework can also be extended to do other tasks. It has built-in support for Redshift clusters, but you can also do other things like invoke system manager tasks to perform actions on servers. You could also use it to trigger security actions like triggering an inspector assessment, any automation of that nature. What if you have a different case where you have a requirement to orchestrate a more complex workflow? Imagine you have an image website or a place where people are uploading images. And as soon as an image is uploaded, you want an image to go through a set of workflow actions. So for example, let's say that a user uploads an image. The image arrives in S3. We have an event notification on that, which triggers a Lambda function. That Lambda function's job is to start a step function state machine invocation. So in the step function state machine, we have a complex workflow that orchestrates the job of multiple Lambda functions. So the first thing this does is it invokes a function to extract metadata from the image. This could be things like the image type, information from the EXIF header, for example. It also then goes and invokes in parallel 2 other Lambda functions. The first one invokes recognition to try to find out the objects in the scene. The second one does an image thumbnail on the object. And finally, all that information is written into DynamoDB using a 4th Lambda function. So the end result of that is when the user refreshes their page after uploading an image, they see all the metadata, they see a thumbnail, and they see the object tags that they were seen in the image. So this is an example. It's actually part of our reference architectures for image processing. And you can use this pattern to extend it to do other things that you want to do upon events. A quick look at the state machine behind this. It looks very much like a flowchart. It has the ability to orchestrate multiple steps. You can have parallel steps, and you can even have error handling. And you can break out if something goes wrong at one of the steps. The other advantage of this is it makes it really easy to add an additional step later. right? So if you decide that you need more processing, you can add that into the pipeline. Let's take a final example here. This is to enforce security policies. So let's say that in your organization, you have a rule that says we should never allow a security group rule to allow RDP access from the world at large. So you can enforce that policy in multiple ways. But here's an example of a way to enforce, detect, as well as mitigate that policy in one step. So the way this starts is once somebody creates such a rule, a CloudWatch event is triggered on any security group changes. That event is fed to a Lambda function, which has custom logic. The custom logic checks against the allowed types of rules and denied types of rules. If a rule is supposed to be denied, it immediately sends an email alert, and then it goes back and makes an API call to delete that rule. So the end-to-end time in which you're exposed is in the order of seconds, right? So it's almost nothing. The other thing you can do in this pattern is you can send those events to an event bus. So you can route them to a different AWS account if you want to. An example of a customer that uses operations automation pattern is Autodesk. They provide software for people who build things. They have many engineering teams who want to launch experimental projects, but they felt that they couldn't innovate fast enough because the amount of time it took to launch a new AWS account and condition it to their security requirements took very, very long and a lot of effort. So Autodesk created a tool called Tailor. As the name suggests, the job of Tailor is to tailor an AWS account to meet the corporate standards. So it configures IAM, it configures config, and direct connect according to the corporate standards. Autodesk has brought the time down from 10 hours of manual work to just 10 minutes. They're doing a lot more projects in parallel now, and the entire framework, Tailor, is available to you open source. So if you have this kind of problem, you can adopt this and extend it by using the source available to you. When you're looking at automations automation, so a couple of best practices. When you're calling AWS APIs, you may get throttled if you make those API calls at a high rate. So handle those using exponential retry backoff algorithms. It's a good idea to publish custom metrics, such as the number of EBS volumes snapshotted, so you can keep track of how that automation is doing over time. Enable X-Ray, as we talked about. And with automation, try to document how to disable the events and triggering to your operations workflow. So if something goes wrong, you can disable that to troubleshoot it. So in summary, we've looked today at how you can use DevOps tools to automate your serverless deployments. We've done a deep dive into 4 main patterns: web applications, data lakes, stream processing, and operations automation. So we highly encourage you to take these patterns home with you to your organizations and see what fits in terms of solving your business problems. And let us know what you can build with serverless and join the serverless revolution. Thank you. We wanted to leave you with some related sessions. The highlight here is SRV317, which is Fannie Mae talking about the HPC workload, and further reading. So these are white papers, which will tell you more about serverless patterns and some of the considerations. So thank you. Enjoy the rest of the show.